Good evening, students. Our today's topic is optical isomerism, and we have already done a part of stereoisomerism, and that is geometrical isomerism. This is the other part, the other type rather, optical isomerism. But before we discuss this optical isomerism, I think you must be knowing that this is very important from examination point of view, and very interesting to understand this optical isomerism. I will tell you an example, and a live example which you see in your daily lives, and that will generate interest for this optical isomerism. What's that? You know, these I'm holding these leaves, and these leaves are that of the spearmint, the mint. They have a good fragrance, a different fragrance. You can feel the fragrance. And on the other hand, keep this in mind, the mint. And on the other hand, I'm having one more thing here, which I will not be able, you will not be able to see, I think. But these are the seeds. These are the seeds, if I can show you. These are the seeds, and these seeds are cumin seeds. Cumin seeds. Zira. तो जीरे का जो है, जीरे की खुशबू जो है, that is different fragrance. They have different fragrance. The mint has a different fragrance. But interestingly, you know, both of these contain the same terpenoid, same compound. ठीक है? What is that? That is carbon. And if I write the structure of that carbon, you see, if I write the structure, it is a 6-membered cyclic structure. You can see 6-membered cyclic structure with a double bond here, and it's basically a ketone, and we have this C double bond O, it's a ketone, okay, and then we have the alkyl link. There is an ethyl link. There is an ethyl link, and here you can see the structure. Okay, there is a 6-membered ring with the double bond inside, cyclohexene. Then actually it is a ketone. Ketone is there. Here you have a methyl group, and then you have a double bond here. Okay, you have a double bond here. This is actually the structure of what, beta? This is the structure of carbon. Now this carbon, if I write this carbon is present in mint, as well as this is present in cumin seeds. Both have the same structure. But they have different properties. You can see the smell is different. And very different. It's not slightly different, it's very different. Okay, on one hand you have the mint, on the other hand you have the cumin seeds. So therefore, what actually this compound actually exists in two isomers, optical isomers. One optical isomer is known as the R isomer, the other one is known as the S isomer. So we have basically two isomers of this. But how can we show those two isomers? They have difference in their atoms and groups with respect to space. So showing that is a very, very difficult task. But I'm going to make that simple for you. How? What I will do, I will be discussing first the Fischer projection. The Fischer projection. I have written here the Fischer projection. When you will know about the Fischer projection, what actually Fischer projection is, you will be able to understand why this mint containing this carbon is different and this cumin seeds carbon is different. How is that different? They have difference in this structure, but in their 3D structure, not the 2D structure, not the planar structure which we are showing on the board. So there will be no difference. They will look alike. They will look alike. So therefore, you must know what the Fischer projections are. So first, I am going to discuss with you the Fischer projections. The Fischer projections. Okay. Then at the end, you will be able to tell me why they have different fragrances. Why these carbons are the optical isomers. So coming to the Fischer projection. So first of all, you must know what Fischer projection is. Fischer projection is basically the representation of, it is a representation of a 3D molecule. A 3D molecule. A 3D molecule means the structure of molecule is 3D. It's not planar always. 3D molecule as a flat structure. As a flat structure. How can we show a 3D structure as a flat structure? That is what is known as Fischer projection. We can interconvert the two. The 3D structure in flat structure, the flat structure into the 3D structure. How can we do that? You have to keep certain 2-3 basic points in mind, and you will be able to see what is the Fischer projection, how we can interconvert a 3D molecule into a flat molecule. I will show you 2-3 things, 2-3 important things which you have to keep in mind. Okay? Once you understand this Fischer projection, it will be easy for us to understand the optical isomerism and the optical isomers. The first thing which you will keep in your mind is that the tetrahedral carbon, which actually when you see methane, I will take the methane molecule, we generally show it like this, C, and we have 4 H's here. If I show this like this, okay. On the board I can show it like this, but actually it is not a flat molecule. It's not a flat molecule. Its hybridization, you know, is sp3. So it is actually a tetrahedral. Tetrahedral. In alkanes, it is tetrahedral carbon. And tetrahedron, you know, I will show you. You all know this is the tetrahedron. So you have a tetrahedral structure. You can see 1 here and the 3 here. So this is they are at the maximum distance from each other, and which gives rise to the structure known as the tetrahedron. So in Fischer projection, what we do actually, this molecule, which is not planar, we show this carbon, tetrahedral carbon, as a cross. Listen to me carefully. Listen to me carefully and see what I am going to show. This tetrahedral carbon, which I am holding here, is shown as a cross. We show it as a cross. See, this is a 3D structure. I'm converting it into a flat structure. How? This structure is shown in the flat structure as this carbon, tetrahedral carbon, is shown as a cross. What type of cross? I will show you. It is shown like this, a cross. Then when it is shown as a cross, then you see we have these groups. These atoms are groups which are connected to this. How they are shown, I will tell you. Firstly, what you can do, see, this is the molecule. I cannot show it on this. I cannot draw it simply on this. So what I will do in the Fischer projection, I will keep these two, for example, these two bonds are there. I will do one thing, they will be coming out. I will keep it, I will hold it like this. You see, these two are coming out and these two are getting in. If this is the surface, if this is the surface, the two are coming out, the two are going inside it. Okay, so on the board you can see the two are coming out, the two are getting in. So what is shown in this picture, those which are, remember, those which are coming out, those which are coming out are shown on the horizontal line. This horizontal line, this is the horizontal line, and on the horizontal line you show those atoms are groups which are coming out of plane, coming out towards us, out of plane. Okay, they are coming out of plane. Then there will be two in number. In the tetrahedral carbon, there will be two in number. These two are coming out. Then those which are getting in, those which are getting in, they are shown on the horizontal, this vertical line. So it means we have four groups which are in this 3D structure. Those which are coming out, if this is the plane, those two groups which are coming out, they are shown on the horizontal line, and those which are getting in, so they are shown on the vertical line. Okay, so we can show this as a wedge dash structure also. How can we show it? Then that will be very easy. If I show this, it's the carbon here, this is the carbon. The horizontal line, on the horizontal line, we have atoms which are coming out. So I will show that with this. This is known as the wedge. This is known as the wedge. So the two groups which are coming out, they are shown by the wedge. Okay. Then we have this line, the vertical line. Then vertical line, we have the two groups which are getting into the plane. They are coming out of the plane. Okay, that is why they are shown by this. This is known as wedge. The line which you show, the solid line like this is known as wedge. And then they are coming out. Remember always, whenever you have this type of structure, consider that, imagine that these two groups are coming out. Then we have this dash. We have this dash. So dash, those groups are atoms which are getting into the plane. So these two groups are, this is known as dash. This is known as dash. So they are getting into the plane, just like the screw. They are getting into the plane. So this horizontal line, wedge, which is coming out of the plane, this is getting into the plane. Okay, so this is how we can show this molecule. But we can also show this molecule in another way. How? See this molecule. We can hold this molecule like this. You can see. Then what you do, keep these two atoms or groups in plane. Keep them in plane. When you will keep these two groups in plane, what will you see? You will see one group coming out, the other is getting in. Two in the plane, two groups in the plane, one is getting out and one is getting in. So this structure can be converted in that also. How? I will tell you. See, I will write the two groups which are on the plane like this. This is the carbon. I am showing these two groups here. These are shown by the simple line, not the dash, not the wedge, but by the simple line. Then we have the two groups, one of which is getting out. You can see that is getting out of the plane. You can see this coming out of the plane. The other one, which is the dash, that is getting into the plane. I can show that like this. So we have now, this is a tetrahedral structure. The two groups, the two lines, which are simple lines, it indicates these two groups are in the plane. The one which is shown by the solid line, it is known as wedge. It means is coming out of the plane, bahir aa raha hai, and this dash line means it's getting in the plane, ye andar ki taraf ja raha hai. So again I will show you again with this model. This is a broken model, I have mended. You can see these two groups, this and this. I can show it like this. These two groups are in the plane, and then these two, one is getting out of the plane, the other one is getting in the plane. So here you are converting a 3D structure. If we will come reverse, this is a 3D representation. Then you can show it by dash and wedge, and then you convert it into the Fischer projection. So this is what is Fischer projection. Fischer projection means you are showing a three-dimensional molecule. Again I will repeat it. What we are doing in Fischer projection, we are representing a three-dimensional molecule as a flat structure. Very difficult, very difficult. Okay, if you will remember this, how can we do it? These two lines, what they indicate, one is the horizontal line, and horizontal line means on this line the atoms and groups are coming out, and on the vertical line they are getting in. I have shown as the wedge dash structure here. Then we can also show it like this. So I hope ye aapko samajh aa gaya, you got this, what I am going to tell you. Now what is allowed in this structure and what is not allowed. So there are 1-2 things which are allowed in this structure, and there are 1-2 things which are not allowed. I will take an example.
Oh, Papa!
See, this is a molecule. I am taking the example of a molecule, and then this is actually lactic acid. You know, lactic acid. And here I have shown it in the 3D form, where you can see the two groups, the carboxylic group and the methyl group, they are on the plane. The hydrogen is, what is happening to the hydrogen? Hydrogen is coming out of the plane, whereas the hydroxyl is getting in the plane. So that means, if I can show this to you, we have these two groups, these are in the plane, one is coming out of the plane, one is getting in the plane. So this is H, which is getting out of the plane, this is OH, which is getting into the plane, this COH and CH3, they are in the plane. So this is how this is shown here. But this can be then manipulated and can be turned into this, where these two groups, generally what we do, these two groups H and OH, we show them on this horizontal lines, and here they are on the wedge, so they are coming out, and then these are going in. So this way I can show you these two groups now, these two groups coming out, these two coming out, and these two getting in. So what I have shown here, H and OH horizontal on the horizontal line, and then this COH and CH3, they are on the vertical line. Generally what we do, the higher priority group, which we will be discussing in a while, that is written on the top, but you can then see there are certain instances where we can just neglect that. Anyways, so this is the structure which I have shown you. Then that can be converted, this structure can be converted now, because you don't need to show these wedges and dashes. Automatically in Fischer projection, the two groups which are on the horizontal line, they are coming out of the plane. Then those which are on the vertical line, they are getting into the plane. So this is the Fischer projection which we have formed from this structure, which is the 3D representation. Now, when you have Fischer projection, what is allowed here? What is allowed? You can play around this structure. How? What is allowed? I will tell you. What you can do if you have this Fischer projection, this molecule shown in the Fischer projection like this, like the lactic acid. We have this lactic acid. Then what you can do? You can just move this molecule. You can move this molecule in 360 degree. Sorry, even 180. If you move them in 360, then you will get the original molecule. But if you will rotate it, you don't have to pull it out in the plane. What you do, you just rotate it by 180. It's allowed. You will get the same configuration. You don't have the different configuration if you will rotate it by, but how much? 180. So that means what is allowed in Fischer projection. In Fischer projection, you can rotate this by 180 degree. 180 degree rotation, but without taking it out of this. In the same this plane, you can rotate it by 180 degree. If I rotate this by 180 degree, what will I get? I will get this group here and this group here. Okay, so I will get this molecule. See what type of molecule I am getting here. I will get this COH here, then CH3 will be here, and these will shift, and then this OH will come here, this OH will be here, and H will be here. This is allowed. This molecule and this molecule, they are identical. Sometimes you may be asked the relation between two molecules here, and in so many entrance examinations such type of questions are asked. What is the relationship between this and this? And you can see when we rotate it by 180, you can see I will just hold it here and will move it by 180. When I will move it by 180, this CH3 comes here, this H comes here, then this COH comes down, and this H comes here, OH comes on this side. So 180 degree rotation is possible. 180 degree rotation is possible. It is allowed. But if you rotate it by only 90 degree, 90 degree or 90 degree or 270, it is not allowed. If you will do that, what you actually get, here we get the enantiomers, which are the optical isomers. So by 90 degree, we are getting the enantiomers. We will come to that in a while. Optical isomerism, we will be discussing that. Here, first we are discussing are not same. They are not same. They are different. They are, in fact, you will see, they are enantiomers. So this is not allowed. This is illegal in Fischer projection. So Fischer projections, you cannot rotate by 90 degree or 270. You can rotate it by 180 or 360. You know that. Therefore, this is not allowed. Okay. Now I will tell you one more example. If I have an example like this, you have a group here like this, OH, and then you have CH3 here. You have then on the wedge, you have suppose CH2OH, and then on the dash, you have H. So you want to convert this into a Fischer projection. What will you do? How will you do that? What is done? Remember, generally an easy way. These two groups, which are shown by wedge and dash, they are shown on the horizontal line. So you show them on the horizontal line. So there is a horizontal line, there is a vertical line. There is a horizontal line, there is a vertical. These two groups can be shown. So therefore, you just do one thing. You write CH2OH and then H. And then these two groups which are in the plane, they are written on the vertical line. So it is OH here and then it is CH3 here. So therefore, we are able to convert it into a Fischer projection. So very easy conversion from this to this. Now in optical isomerism, we will come across these type of structures where we have wedge, where we have dash, or we have this Fischer projection structures, and both of them will be dealt accordingly. Now coming to the main topic, that is optical isomerism, and what is optical isomerism and what are optical isomers. See, these are actually two compounds having same molecular formula, but their approach towards the light optics, as the name indicates, is in fact different, in fact opposite. Approach towards light. Which light? A specialized light, which I am going to discuss here. See, if you have ordinary light, this ordinary light can just see, this is the ordinary light. It can move in all the planes. So this is an ordinary light. Now you pass this ordinary light through a Nicol prism. If you pass it through a Nicol prism, which is made of calcite, calcium carbonate, then when it comes out of this prism, there's a different prism than what you see, a triangular that which separates the light into 7 colors. Is a different type of prism, Nicol prism. When you pass this ordinary light through it, what happens? This now propagates in only one plane. This light is known as PPL, that is plane polarized light. Plane polarized light. Plane polarized light, PPL. Then this PPL, when we pass this is different from monochromatic light that has same wavelength. This is different. When this is passed through solution of a compound, suppose an organic compound, the solution of an organic compound, what that organic compound can do, that organic compound or even inorganic compound, that has the capability, some of them, not all, to rotate this plane polarized light. Its plane is rotated either towards the right or towards the left, or there is no change in the plane of polarized light. See, when we pass through this organic compound, either this plane is rotated towards the right or this plane is rotated towards the left. Okay, either towards the right or left, or there seems to be nothing happening, no change. Okay, 3 cases here. Either the plane of polarized light tilting towards right or left or nothing happening. If it is tilting towards right or left, that means this compound is interfering with this light. So such compounds are said to be optically active. these compounds are optically active. And that compound which does not, the solution of which does not interfere with the plane, that is said to be optically inactive. Or in later in this case what you see, it can also be a meso compound or a racemic. So that we will take up separately at the end, meso or racemic. Right now just see, when it rotates towards right or left, it is optically active, and when it does nothing, it is optically inactive. So therefore we can have organic compounds or other compounds categorized into two on the basis of whether they respond to PPL or not. There are compounds, therefore the organic compounds can be categorized into two. One is those which are optically active, and the others are optically inactive. We are interested in this category, optically active part. Those compounds which are optically active rotate the plane polarized light towards the right or the left. Then the question arises, why some compounds are optically active while others are inactive? That we are going to take up. What is the fundamental thing which these optically active compounds contain, and that is lacking in the optically inactive compounds? That very basic thing is that optically active compounds, when various experiments were carried out in this is known as polarimeter. This whole arrangement is a polarimeter. When this plane polarized light was passed through certain organic compounds which rotated it, then it was felt that those compounds have a basic thing. What is that? Those optically active compounds do not possess any element of symmetry. They don't have any element of symmetry. That means they are lacking a symmetry. They are not symmetrical. They are not symmetrical. Optically active compounds, whatever compound was there, or whatever compound was there which was optically active, that showed no element of symmetry. There was absence of elements of symmetry. What are then elements of symmetry? Elements of symmetry are plane of symmetry, center of symmetry, plane of symmetry, then you have the center of symmetry, and you have the what is known as the axis of symmetry. We have alternating as well, but we'll take up that later. Axis of symmetry, three basic elements of symmetry: plane of symmetry, center of symmetry, and axis of symmetry. See, what is plane of symmetry? Plane of symmetry is, if you have a compound, if you have anything that can be divided into two equal halves, that means it has a plane of it has a plane of symmetry. Suppose this marker is there, you can cut it here into two equal halves. Therefore, this possesses plane of symmetry. We have this. You can see this plastic thing is there. So we can just cut it like this, and we can have two equal halves. So anything that can be cut into two equal halves, that has a plane of symmetry. Like we have this circle. You cut it here, you have two equal halves. Then another one is center of symmetry. Center of symmetry means when you have any compound, and there is a center, and then suppose I will show it like, I will show it here. Then I have a compound like this, and there is A, then B, then B, and this is, suppose this is the compound. Now what I will do, I will take the center and then move towards this, and at some distance I get A. In the back of this direction, you see the same compound, the same thing at the same distance. If such is the case, we say the compound is having a center of symmetry. So that is center of symmetry. And then comes the axis of symmetry. Axis of symmetry, what is the axis of? Axis of symmetry is an imaginary axis on which if you rotate the compound by certain degrees, 90 degree or 120 or 180, whatever, then you should get the same